So it's time for us to do some problems involving finding volumes by looking at cross-sections, in particular the disk and the washer method. Now, as we're doing the problems, pay particular attention onto the setup of the problems. In some sense, the integration is secondary at this point. What we really want to focus on when we're talking about applications is figuring out how do we get to the point where we have an integral that represents what we're looking for. So make sure you practice that. And in particular, if you're following along with the video, consider making frequent use of that pause button. And when you see a problem, pause it and think about, what do I do? What's the next step? Then try it. Unpause and let's compare. And the more you do on your own, the better that you get. And we think you're going to be amazing. So keep at it. All right. Well, let's begin. So our first problem. Let a solid be formed where the base of the solid sits on the xy plane over the region where x goes between 0 and pi over 3, and y goes from 0 to secant x. So that's down here. So let me point out where we're at. So this part, this shaded part, is the part what it's talking about. So this is the x and the y. So here we are at pi over 3. So if you were to sketch secant x, it's this curve right here. So now this shaded region, that's our region that we're over. Okay, now that's in the xy plane where we're going to go and make a solid. So we need to have, how are we building our shape? So here we go. The cross sections of the solid, which are perpendicular to the x-axis, are squares. So it's actually drawn some of these cross sections already for us. You see, we're perpendicular to the x-axis. So here's the x-axis. So we slice, and what we want to do is we want to be up and down, perpendicular to that. And you say, okay, look, there's a square here. So this is one side of the square. And then you just say, well, once you know one side, you can find the other three sides fairly straightforward. And there's one cross section. There we go. Now what happens is that as we move along the x-axis and we take different cross sections, we're changing the size of the square. So at the very beginning, it's kind of a small square. By the time we get over to the end, it's become a much larger square. So our shape is changing as we move along in the x direction. All right, so that's our setup. And the question, determine the total volume of the solid. All right, good. Now, how do we approach this problem? Well, we can think about by saying this is describing what cross-sections look like. This is not something that's done by a volume of revolution. Oftentimes we have a very specific set of tools for that, but that would require things that look like circles. There's no circles, these are squares. So we say, okay, our volume should be found by adding up the little pieces of volume. So we're going to say our volume is going to add up, which is our integral, from wherever we start to wherever we end. Then we're going to have the area of our cross-section and the thickness of our cross-section. So what happens is if we take area times thickness, that's the volume of one little piece. And if we add up the volume of the little pieces, we get the total volume. So we need to sort of fill in our parts. Where do we begin? Where do we end? What's our area look like? What's our thickness look like? Put it all together, and we have our setup. And that's really the majority of the problem, is getting things set up. Because once it's set up, from there it's a nice, relaxing day of integration. Okay, so let's think about it. Well, our thickness, that's usually pretty easy. We think about, what does our thickness mean? Well, in terms of the picture, we think about, well, we're just perturbing our cross-sections. See, our cross-sections are when we're perpendicular to the x-axis. So what we want to do is we want to move along the x-axis. So it's the x-axis that's going to perturb. So the thickness is a dx. Now how about the area? Well, for that we say, well, what are our pieces look like? What are our cross-sections? They're squares. Okay, well, how do you find the volume of a square? Well, you take the length of one side and you square it. It's not a coincidence that we use the square that way. Okay, so I just need to know the length of one side. So if I'm at a given x, the question is, how long is the length of that side? Well, what's going on? Think of the picture. See, the side is going between the two curves. This curve down here, that's the curve y equals 0, and this curve up here, that's the curve y equals secant of x. So the length of the side is the distance between 0 and secant of x. So our length is secant of x. So that's the length of one side. So the area will be the secant of x squared. All right, good. Now, where do we start and where do we stop? Well, where do we start and stop at 0? Where do we start and stop x? From 0 to pi over 3. So we have start at 0, go to pi over 3, and we're going to integrate secant squared of x dx. That's our setup. Good. Now ready to go. So we ask ourselves the question, do we know how to integrate secant squared? And the answer is, this is a great one, because secant squared isn't just any function to integrate. It's one of our really basic functions that we have memorized. It's, I would say, definitely makes the top 10 of things we should know. So the integral of secant squared, or if you like the antiderivative of secant squared, is tangent. So this is tangent of x evaluated from 0 up to pi over 3. So that's going to be tangent of pi over 3 and subtract tangent of 0. Well, tangent of 0 is 0, so that's good. That goes away. Tangent of pi over 3. Well, do we know what that is? Well, it turns out pi over 3 isn't just any angle. It's a rather nice angle. And so if you think about what it is, it's if you're more comfortable with degrees, it's 60 degrees. And if you think about what happens in a triangle, so let's suppose we start with an equilateral triangle. So this angle right here, that's a 60-degree angle right there. So if this side has length 1, then you could imagine dropping it down. This side would have length 1/2, and this would have length square root of 3 halves. So what happens is when you take the ratio, opposite over adjacent, you end up with square root of 3. And that's the answer. Our volume is square root of 3. Now you might say, square root of 3 what? What are my units? And, well, they didn't give us units. So we're just going to put square root of 3. Now if they had said, where everything is measured in feet or meters or whatever, then we could talk about what the units are. But for now, square root of 3. Good. What a fun problem. Nice. So let's hope we have some more fun problems. And of course we do, right? It's calculus. All the problems are fun. So another problem. Find the volume of intersection of two cylinders of radius 1 where the intersection is at a right angle through the centers of the cylinders. And so here's sort of a picture to help us think about what's happening. So it's like you have a pipe running one direction, and then perpendicular you have a pipe same size going the other way. They intersect. What's the volume of the overlap? Well, our initial response is, it's not so easy to visualize what this shape might look like. And so we have to start thinking. And the first thing we have to start thinking about is, all right, how should we slice? Because our sort of idea right now is we should take this shape and we should slice it up. And if we can slice it up in a nice way, then we can make progress. Now you might say, well, what do you mean by nice? Our goal is when we talk about taking slices is to make sure that the shapes that show up are things which are easy for us to understand. And that's what we mean by nice. Easy to understand, easy to work with. So, how to slice? That's the big question. Now, one way to think about it, well, of course, there's always the try something, and if it doesn't work, try something else. But let's think if there's sort of a natural thing that's happening here. So what do we have? It's a three-dimensional thing, right? Because all volumes are three-dimensional. We have something going up, down, say something going left, right. So in my perspective, it makes sense to say, well, let's move back and forth in that third direction. So in other words, slicing as we move backwards and forwards. And let's see what that gives us. All right, so what is happening there? Well, what I'm talking about, you can imagine that, suppose I were to look down, straight down one of the pipes. So here I'm looking straight down the center of the pipe, and I'm going to slice as I move forward and backward. In this case, it would be up and down because we've changed our perspective. So when you slice at a particular height, what do you see? Well, so we take our slice, and what we see is we're going to see a line segment at that particular height. So in particular, suppose we take that idea and put it onto this diagram right here. So when I go at a particular height, I'm going to see the following. So from one cylinder, I'll see this shape here. So that's taking this thing onto that cylinder. From the other cylinder, I'm going to see similar thing, that shape there. So this is now just a flat thing. So what I see is when I'm slicing, I'll get what looks like a plus sign. Now, what's the thing we need to focus on? What we focus on is the center of that plus sign, this piece where they overlap. And the question becomes two questions. First off, what is that shape? And once we understand that shape, what's the volume of that shape? Well, what do we see here? The answer, we see a square. It's going to be a square. The nice thing is the two cylinders are the exact same size. So that when we slice here, we're going to get the exact same length in both cylinders showing up. So that their overlap is going to be a nice square. Now, if the cylinders had been different sizes, we'd get a rectangle. Well, that's still not so bad. So we're back to squares again. Squares are lovely things. So now we feel like, aha, we're making progress. All right, good. So what's the next thing for us to understand? Well, now that we understand that we have a square, the next thing for us to understand is what's the area of that square? So we need to start thinking about how to find the area, which for us really boils down to height. Because, well, I said height. I really should have said length. So why? Well, I just need to know the length of one side, and I need to square. Now, the reason I'm talking about height is we know we have a radius 1. So we should think about moving up and down. So let's put kind of a very straightforward idea. We'll put 0 here. We'll put 1 up here. And we'll put -1 there. So we're moving between 1 and -1 as we take our slices. And, well, we'll call this y. Why not? All right, so here's y. So now, suppose I'm slicing at a particular value for y. The question is, how wide is that? Okay, so let's draw a little bit bigger, and because I think we'll need to see the picture a little bit better. All right, so here we have y equals 0, and now I'm here. Here's y, and the question becomes, what's true about that length? Well, we know it's a unit circle, and so we have our really good rule for unit circles, which is x squared plus y squared equals 1. So I can actually figure out, okay, what is x in terms of y? So this tells us that x squared is 1 minus y squared, which we can rewrite that as x is plus or minus the square root of 1 minus y squared. Now the reason we get two possibilities here is there's really two sides, because there's this right-hand side, which tells us that over here, x would be the positive part, square root of 1 minus y squared. And then over on this other side, that's the negative side. So this would be x equals minus the square root 1 minus y squared. So what's the length between? Well, we combine. And we say, all right, well, it's this value of x, subtract that value of x, or it's 2 square root 1 minus y squared. So that's the length of cross. Now we're ready. We have all our pieces in place. So what do? We know that to find the volume, we're going to add up the individual areas times our little thickness. So our setup is the following. Our volume is the integral a to b, start to stop, our area of our cross-section times our thickness. Now, the way we're thinking about it is we're really thinking about it as y varying. So our thickness is going to be a change in y. All right, it's perfectly fine. We don't have to use x as our variable all the time. We can use whatever variable is convenient. In fact, we always should focus on saying what's convenient to use, and let's use that. All right, so good. We're making progress. Now, the area. We know it's a square, and so to find the area of a square is you take the length of one side and you square it. Well, that's our length, 2 square root of 1 minus y squared. So 2 square root 1 minus y squared. All right, now we're almost there. Finally, our integral. What is that? Well, where do we start? Our y goes from -1 to +1. So there we go. Now, what can we do? Well, square that. So that's 4, 1 minus y squared dy. We can save ourselves a little bit of work if we pause and say, hey, let's make an observation. You see, this object has symmetry. In other words, think about it this way. I'm going between -1 and +1, which says if I look at what's happening in the top half, that's going to match what happens in the bottom half. So in other words, I have these two sides, from 0 to +1, from 0 to -1. They're going to be equal. So what I can do is I can say, well, look, I'll just compute one of them and double. In essence, what's happening here is that we have an integral of an even function. And so I can sort of cut it in half and double it whenever I have this symmetry from a negative value to a positive, same value, even function. So if we did that, we could say, all right, this is the same as double, so we already have a 4, double that gives us 8, integral 0 to 1 of 1 minus y squared dy. Now we're ready to go. That's a polynomial, one of our favorite things to integrate. So we have 8, integral of 1 is y, integral of y squared is y cubed over 3. So y minus 1/3 y cubed, evaluate from 0 to 1. Now the nice thing is because we have 0 involved, 0 is wonderful to work with. And as often as you can, you should think about how can I get 0 involved in my problem? Because when you plug in 0, you get 0. So we really just have to plug in the 1. So we end up with 8 times 1 minus 1/3. Well, 1 minus 1/3 is 2/3. And then times by 8 gives us 16 over 3. And there we go. That's the answer. Beautiful. Now, one of the things that's surprising to me, there's no pi. Because oftentimes whenever we see problems of things that involve circles or round objects, we often expect that there will be a pi involved. But this one, there wasn't a pi. And it just worked out that way. And that's okay. That's okay. Sometimes math is beautiful that way. All right, good. Well, on to another problem. Of course. So here we go. Let R be positive, and it's a fixed value. We want to find the volume of the solid formed by rotating the region between the x-axis and the curve y equals the square root of r squared minus x squared about the x-axis. So in other words, you see there's this top half of a circle. So this is a circle of radius r, and we're taking this top half, and then we're going to spin it. And we still want to say, well, what's the volume? Well, what should the volume be? Well, note, this is going to make a sphere. And so we say, aha, this should be the volume of a sphere. And, well, what's that? Well, we're going to prove it's 4/3 pi r cubed. And we're going to use calculus to do it. I will say there's ways to prove that the volume of a sphere is 4/3 pi r cubed without calculus, but we want to use calculus, right? Because we have these beautiful calculus tools, and we want to be flexing our calculus muscles right now. All right, so let's think about what's happening. Well, what we need to do is think about how do we form our shape. Now, in this case, we're forming it by spinning it around the x-axis. So as we're forming our shape, one way we can think about it is let's start and see how a piece of it gets formed. So I can say, let's take a very small piece, and I'm just going to take this little piece right here. So here's my small piece, and I'm just going to spin this small piece around. And the question becomes, well, what shape is getting formed? And the answer will help guide our way to solve this problem. And what we see showing up is we see, aha, this is a disk. In other words, it's a nice circle, is our cross sections. Say, perfect, perfect. All right. So we're going to do our disk method. Now, how does the disk method work? Now, the way that the disk method works is it says the following. We're going to say our volume is going to be adding up, which is integration. So we have our integral from wherever we start to wherever we stop. And then we're going to have pi times our radius squared. And then we're going to have our thickness. So this is the way I like to remember the disk method. It's sort of, I'm not writing in terms of functions. I'm saying, what does everything represent? Because if I understand what things represent, then I can say, okay, this is what thickness is. This is what the radius is. And I can put in everything in the right place. And I'm easy to adapt to new situations. So we think to ourselves, all right, well, let's think about things. Well, the thickness. The thickness is going to be a small change. So our thickness here, our small change is going to be dx. We're just, how much does x change as we perturb it a little bit? How about our radius? Well, what's that? Now, you might say, hey, isn't it a radius of the sphere? Is radius r? No, no, no. Think of it, the problem. The question is, what's the radius in that slice? All right. So our radius is this length right here. That's our radius. You'll notice it's not fixed at one value. It changes. Over here near the edge, it's very small. In the middle, sure, it's large. And then, of course, it goes in between. It just depends on where we're at. Now, in general, it's going to be the distance from the point where we're spinning up to the curve. So it's this length right here. That's our radius. So in our case, it's up to the curve there. So that's the square root r squared minus x squared squared. All right, good. And then our bounds are from negative r to positive r. But let's use symmetry just like we did in a previous problem. That says, hey, if I were just to start and just do the from 0 to r, the right side here, that would be the same as if I did from negative r to 0, because the shapes are equal on both sides. And so we say, okay, so let's take advantage of that symmetry. So I'm going to double, going from 0 up to r. I have the pi. Now that's a constant. Let's go ahead and pull that out as well. The square root of r squared minus x squared, squared. All right, that's r squared minus x squared. And then, of course, dx. All right, good. Now we're ready. So we integrate. And let's be careful here because we have two symbols floating around. There's the x and the r. And we want to make sure we don't get confused about what's happening. So recall, r is a fixed value. So we treat it like a number because it is a number. We just don't happen to know what that number is. The x is the unknown. It's the part which varies. So when we integrate, for example, r squared, well, that's just like integrating a number. And the way that you integrate a number, well, it's that number times the variable. In our case, it's x. The integral of x squared, because we're integrating with respect to x, well, that would be 1/3 x cubed. And evaluate 0 up to r. Again, 0. Ah, what a lovely number. It's great to have 0 involved when you can. When you plug 0 in, you get 0 out. Beautiful, beautiful. So we need to plug in r. So we get 2 pi. So we have r squared times r. Well, that's r cubed minus 1/3 r cubed, which is, r cubed again. So you'll notice it's r cubed in both. So then you have 1 minus 1/3. Well, that's 2/3 times 2 gets us to 4/3. We have the pi, and then we have the r cubed. 4/3 pi r cubed, which is what we said we'd get, right? Look, woohoo, it matches. So we did something right. At least that's a good sign that we probably did something right. So this is one way to derive the formula for the volume of the sphere. Like I said, there are other methods that are more geometrical, but it's kind of nice to see it. It's nice to know it's like, no, it's not just a formula that somebody told me. Now I know why it's true. I can give a complete justification, and it's a beautiful, beautiful thing. All right. Well, let's try another problem. Next problem. Find the volume formed by spinning the region bounded by y equals x squared and y equals 2x around the x-axis. Then there's a question. How does the setup change if we spin it around the line y equals -1? All right. Well, so now we have two parts. We have to find a volume, and we have to say, well, wait, what changes? All right. So let's start with the first part. Let's find the volume. Now here, there is no picture, so we got to provide one. So let's start. We'll draw some axes here. So draw some axes. We have y equals x squared, and that looks a lot like a parabola. Well, mainly because it is a parabola. That's a good reason why it looks a lot like a parabola. So here we go, y equals x squared. And then we have the line y equals 2x. Now y equals 2x, well, it's a line. It's a little steeper because it's 2x, so okay. Goes through the origin, y-intercept is 0. Yeah, it looks something like that. So here's y equals 2x. And remember, we're spinning it right now around the x-axis. Okay, so we're spinning it that way. So that's our shape right there. Okay, so there we go. We're taking that little region, spinning it around the x-axis. Now, what do we need to do? Well, we need to start understanding a couple of things, such as where are our bounds? You know, we have curves, but somehow we need to get appropriate bounds. What do I mean? Well, let's look at for where the curves intersect. Now, one is pretty easy to see, and that's over here at the origin. So that's 0, 0. How about up here? Well, when does that happen? That happens when x squared equals 2x. Now, we can move the 2x across. X squared minus 2x equals 0, or x times x minus 2 equals 0. Well, we already know about the x equals 0. That's what gave 0, 0. It's a good thing that we actually saw it again. X equals 2, that must be this one right here. This is at 2 and 4. All right. So now we know, in some sense, that helps us figure out where to start and stop. We're going to start at 0, and we're going to end at 2. Okay, good. Good to know. Good to know. So the next thing for us to figure out, now that we know where to start and stop, is we have to think about what's the shape? And in particular, you know, what tool do we need to use? Now, I like to think about it by saying, let me think about what's happening to a small slice. Because this is a volume which is done by spinning. So if I think about, well, let's spin a little piece, and that will help guide us in understanding what's going on. So I'm going to say, well, let's suppose I just take a little piece, there's my little piece, and I spin it. And what happens to that piece as I spin it around? Well, what happens is I get a shape. And this shape is a washer. In other words, it's a big circle with a little circle in the middle that's been punched out. So I say, aha, this is going to use the washer method. Okay, so how does the washer method work? Well, really, one way to think about the washer method is you find a volume of a big piece and subtract out the little piece that's the whole. But the way we oftentimes write it is in the following. We say, okay, the volume would be equal to the integral a to b, which really says adding up from your start to your stop. That's what integration is, adding up from where you begin to where you end. Then we're going to have a pi, and pretty often whenever you see a volume formed by spinning, you should expect a pi to be involved. And what else? Well, you really have two circles. So you have your big radius, which is, another way to say it is your outer radius squared, minus your small radius, which you could also say is your inner radius squared. So big circle minus little circle, and then you have your thickness. All right, so now we just have to sort of start digging into everything and saying, okay, what is this? What is that? If we understand all the pieces, then we can put it all together. All right, so let's think about what's happening. Well, where do we start and stop? Well, before I answer that question, let me just focus on saying, how are we cutting things up? Because that's important to understand. Remember that this was our little slice here. And so what was happening was our thickness, our small change, was really a small change in x. So that says our thickness is our dx. So when we talk about start and stop, we should really say, well, since we're slicing with respect to x, we start and stop with respect to x as well. So we're going to start at 0, because that's where the shape starts, at x equals 0. We're going to end at 2, because that's where the shape stops when we look at the x value. Pi is a number, not much to do there. Okay, so we have our other pieces left. The big radius, the little radius. So how about the big radius? Well, the big radius is from where you're spinning, now that's the line y equals 0, up to the furthest one away. So the big radius, let me choose a slightly different color. I mean, we have different colors, right? Take advantage of color technology. So our big radius is this length here, right? From the spinning up to the outermost curve. So in this case, the outermost curve is the 2x. So that's the big radius. How about the small radius? Well, you still go from where you're spinning up to the closer, the innermost curve. So that distance from 0 up to x squared is x squared. So what we end up with is we end up with the following. We have the integral 0 to 2. Pi is a constant, so let's go ahead and bring that outside. Pi out in front. Then we have the outer radius squared. So that'll be 4x squared. Then minus the inner radius squared. So it's already x squared, so x squared squared, x to the fourth. So minus x to the fourth and dx. Good. Our setup is done. Now, carry it out. So, pi, and then what? The integral of 4x squared would be 4x cubed over 3, because you add 1 to your exponent, so right, x cubed, and then divide by the exponent, so that's why we divide by 3. Minus, okay, add 1, x to the fifth, divide by that new exponent, 5. Evaluated from 0 to 2. some good news. It's not so hard to plug in 0. 0's beautiful. It won't always be trivial, but oftentimes it is. See, 0 cubed, 0 to the 5th, 0. Gone, gone, gone. All right, which means plug in 2. Now, 2 cubed is 8. 8 times 4 is 32. So we have pi 32 thirds. 2 to the 5th. All right, powers of 2. So let's start. 2, 4, 8, 16, 32. All right, so 2 to the 5th is 32. Again, 32. Wow. Okay, so 32 thirds minus 32 fifths. Well, 32 is common, so we can pull that out for a second. So let's see, we have a 32 pi, and we have 1/3 minus 1/5. Now, if you were to put those together, well, common denominator would be 15. So we could say that this 1/3, I can replace this as 5/15, and this 1/5, 3/15. So 5/15 and subtract 3/15 would be 2/15. Well, 2/15 times 32 would give us 64 pi over 15. Now, 64 does not have anything in common with 15. So that's as simple as it gets. Now let's pause for a second here, because there's one thing we should say. We are after a volume, which is a measurement, which means that our final answer should be positive. Now, luckily, we got a final answer which is positive. What would have happened if our final answer had been negative? Well, that means a mistake was made. Now, what is a common mistake? Well, you may have accidentally swapped what the radiuses were. Maybe you said, it's x squared squared minus 2x squared. And you might say, well, okay, I'll just change the sign, life is good, and no one will notice. Well, be careful. Depending upon how it's being graded, it might be caught. But another thing that might have happened is maybe you did a small calculation error when you did your integration. Because small errors do happen. Believe me, I'm really well aware that small errors happen. I make them all the time, and I try to do a better job of catching them. So anyways, the point is, if you do end up with a negative answer, you should stop and say, something went wrong, either in my setup or in my computation. So let me take this chance to go back and check my work and make sure I get an answer which is reasonable. Because answers should be reasonable. So that's a great way to sort of keep it in mind of checking your work. If you get unreasonable answers, and we'll see examples of this as we go along, something has happened and we need to fix it. All right, now keep in mind we're not done with our problem yet. There's a second part. So remember, how does the setup change if we spin it around the line y equals -1? So what's happening there? Now let's think about it. So I'm going to draw the picture again, just sort of simplify it a little bit, just so we can sort of talk through the process. All right, so we have our shape. So we have our y equals 2x, y equals x squared, and we have this piece. So that's the little region. And then we're going to spin it around the line. Let me move this up just a touch. And now we're going to spin around not the axis, but here around y equals -1. So the question becomes, what changes in our setup? Well, our basic idea of let's break things into small parts, that doesn't change. So we say, all right, we still have our small piece, and we still spin it. When we spin it, it's still a washer, but what's happened to it? Well, essentially what's going to happen is instead of a washer that looks like that, it's going to stretch out a little bit. Because now, here's the key thing, is that our radius, that's the part that's changing. We're not going from the top down to the x-axis, we're going all the way down to -1. So, what do we have? Well, what happens is I now need to find the length from this curve, which is y equals 2x on the top, down to the curve y equals -1. Similar process, you say, okay, our inner radius, we don't go from x squared down to 0. We go from x squared down to -1. So we have to think about, okay, what's that radius? So now we are ready to work through the change. So we have the following. Our volume, we still start and stop at the same place. So it's still going from 0 to 2. There's still a pi, because that's part of our setup. The part that's changing is our radius. So it will become this length from 2x to -1. Well, the way you find it is you subtract. You take high value, subtract low value, top minus bottom. So 2x subtract -1 would be 2x minus -1, also known as 2x plus 1, quantity squared, minus, and now again, we're going to take the radius of the inner part, x squared down to -1. We again subtract, high minus low. X squared subtract -1 becomes x squared plus 1, quantity squared. And then our thickness still is dx. So that's how our setup changes. It's not so bad. It really is just going to become an integration with the polynomial again, but it's important to see what's happening. What's happening is as we adjust which line we spin it around, the part that changes in the setup is the radius. And so we need to keep that in mind. All right, good. Well, let's try another problem, right? Of course we should. Okay. Find the volume when the region where x goes between 0 and pi halves, and y goes from sine of x, so that's this bottom curve, and 1 plus cosine of x, which is this top curve, is spun around the x-axis. So they've done a lot for us. They gave us a picture. We see where we're spinning. Life is good. Okay, so what's going to happen here? Well, I think this one probably will not have too many surprises. We have our shape here, and what we're doing, well, we're going to think about what happens to one slice. So here's a little piece. We spin it, and as we spin it, what shape do we see emerging? You see, that shape that emerges as we think about what happens to one slice, it tells the story of what we should do to answer the problem. And in this case, the shape that we see emerging is it's a washer. So we're going to use the washer method. All right, good. So where do we begin? Well, let's begin with writing down our basic formula. So our volume is equal to adding up, which means integrating, from where we start to where we stop. We have pi, and then we have our pieces, our outer radius, which I'm abbreviating as capital radius, but again, we could write outer radius if we wanted to, and then our inner radius, and again, we could write inner if you wanted to. Outer radius squared, inner radius squared. Really, it's big circle area minus little circle area, and then our thickness. All right, so that's our formula. That's our setup. Now we have to start thinking about our pieces. Okay, so where do we start and stop? Well, we can see it. We're going from 0 to pi halves. And we also, of course, should have really focused on thickness first, but our thickness we can see is we're really saying perturb x a little bit. See, because that's the thin part. So that's our small perturbation. All right, so our thickness, this part, looking ahead, will become our dx. Now, our pi, that's always going to be there. What's our outer radius? Well, we want to go from where we spin around, that's 0, up to the top curve. Well, we know what the top curve is. It gives it to us. It's 1 plus cosine of x squared minus our inner radius. Okay, so from there to there. So that's sine of x. So that's our distance. Again, squared. And then dx. Good. All right. So I think we have all our pieces in place. figured out start and stop. We know our thickness, pi, outer radius squared minus inner radius squared. Life is good. From here, it's do an integral. Okay, well that sounds like fun. So let's see where we go. So we can pull out the pi. Sure, of course. And then we do what? Well, we probably have to square. So square 1 plus cosine x would be 1. Then you have the middle term, 2 cosine x. And then the last term, cosine squared x. So if you're wondering, where is that coming from? It's a plus b squared, right? It's a squared, 1 squared, 2ab, that's the 2 cosine x, and b squared, cosine squared x. So that's the 1 plus cosine x quantity squared, goes down to that piece right there. Subtract sine of x squared, well that's sine squared of x. Okay, that one's pretty easy to spot. All right, good. Now here, we're very lucky there's only one term. Be careful. Minus signs are, oftentimes students make mistakes because if there had been more terms, don't forget that minus sign would need to distribute through to all the little pieces. That's a very common mistake, so we want to pay attention, and I'm sure we'll talk about that in future examples. At some point, it always comes up sooner or later. And when it comes up, we're going to be prepared and say, aha, you can't catch me this time. Not this time. Now, let's see. What are we happy with? Well, 1, we're happy. That's easy to integrate. That's what I mean by happy. What are things where we can integrate? Cosine of x, beautiful. We know how to integrate that. Cosine squared. No, don't know how to integrate that. Not really. Sine squared? Kind of similar. Now you might say, ooh, cosine squared and sine squared equals 1, right? Right. Yeah. Well, cosine squared plus sine squared does equal 1. This is cosine squared minus sine squared. Is there anything nice about that expression? Is there? Is there an identity involved? Well, there is. In fact, there's about 6 trig identities that you should know, and one of them involves cosine squared minus sine squared. All right, so let's see. Do you remember it? Okay, it is cosine of 2x. In other words, it's a double angle formula for cosine. And now we're happy because cosine 2x is something we know how to integrate. So we say, all right, beautiful. So we'll rewrite it one more time before we integrate. So pi integral 0 to pi over 2, 1 plus 2 cosine of x plus cosine of 2x dx. All right, so here we go. Pi integral of 1 x. Nice. Integral of cosine. Sine or negative sine? Okay, let's be careful. Is it positive sine or negative sine? It's positive sine, yeah. See that? Cosine and sine, because, there's that little tricky thing. When you differentiate one versus when you integrate one, you got to keep track. Well, where does the positive and the negative come up? So it's the integral of cosine is positive sine. The differentiation of sine is positive cosine. So, okay, how about cosine of 2x? Well, integral of cosine would be sine, positive sine. And so you end up with sine of 2x, and then you just have to account for the 2. Now, because 2 is a number, this is why we can get away with this. You do it by multiplying in front by 1 over that number. So half. So we're almost there. We're going to go from 0 to pi over 2. Now, we start by plugging in pi over 2. So what do we have? Well, we have pi times pi over 2 plus 2 times sine of pi over 2. Well, sine of pi over 2, sine of 90 degrees, that's 1. So plus 2. Sine of 2 times pi over 2, well, that's sine of pi. And sine of pi is 0. Nice. Cool. Now we subtract, plug in 0. So plug in x equals 0. Well, that's 0. 2 times sine of 0, 0. Sine of 0, 0. Very zero-y. Lots of zeros. So it's all zeros. Good. So that's 0. Aha! Nice. So our final answer, we can say, is 1/2 pi squared plus 2 pi. Right? Because pi squared over 2 and 2 pi. And that's the answer. Nice. Good. Good. Good, clean fun. These problems are fun. Okay. Well, probably should do one more. One last problem to finish this up. Take us home. Okay, so what is it? Find the volume of the shape formed by rotating the region where x goes between 1 and e cubed, and y goes from log x to 3. Around the line, x equals 1. What? This will be interesting. Okay, so let's think about what's going on here. So first off, let's sketch and see what we have. So we have 1 all the way up to e cubed. So let's say, let's put this as x equals 1. And x equals e cubed, I'm not sure exactly what e cubed is. It's kind of a biggish number. So let's say it's out here somewhere. It's definitely bigger than 1. Okay, good. Now, log of x. Well, probably we should think about what's happening. So let's think about what happens at 1 and e cubed. What's log of 1? Log of 1 is 0, so it's going to cross here. What's log of e cubed? Well, the nice thing, log of e cubed actually is pretty easy to compute, because what you do is that 3 can come down. So it's the same as 3 times natural log of e, and natural log of e is 1, so you really end up with 3. So it's going to be, over here, 3. And so log x is going to come up and do something like that. Okay, so here's our curve, y equals natural log x, and 3. Oh, whoa, hey, look, wow. It's almost like they knew we were going to need it. Okay, so here we have y equals 3. All right, so our region now is what? Well, it's kind of this, almost a triangle. It's not quite a triangle. Our problem here, the reason I say it's not a triangle, is while 2 of our sides are nice and flat, there's that one side which is a little bit curvy. So, but triangle-like. Now, what makes this interesting? Where are we spinning? We're spinning around the line x equals 1. In other words, this way. So if you've been following the other problems along so far, it's sort of spinning perpendicular to what we've been doing before. So, interesting. I wonder what will happen here. Well, all right, so what will happen is we'll go off and we're going to spin. Now, we have to start thinking about, what do we do? Well, what do we know? We know how to find it when our cross-sections are nice. And we might say, well, how do we take cross-sections? That's an important question. Do we want to take cross-sections like this? And the answer is no, not that way. That way wouldn't work. At least we don't know what the shapes are. Because when I take a cross-section, in other words, when I slice that way, there are all sorts of weird varying shapes, and it's not clear what things look like, and it definitely would be a hard thing trying to find the area of those shapes. Okay, well, what can we do? Well, let's just change the way we slice. We get to choose that, so let's choose something that works for us. So the other natural way is to slice that way. Now notice what happens. If we slice that way, then what happens, we can think of it as though we're taking a small little piece like this and we spin it around. And lo and behold, what do we see? Well, what we see is a circle. So our slices, when we choose the right way to slice, are nice. So this is a good rule of thumb. Always choose a way to slice so that your pieces are nice to work with. It's almost like we care about ourselves, because we do. We love ourselves. We want to make sure we give ourselves the best chance to succeed, because that's our goal in life, is to succeed. All right, so now we've got to start thinking about our setup. Because we've swapped our way we slice, if we were too tied into a formula, it might be hard for us to adjust. But now, remember, we're not tied into like, oh, it's f of x squared. No, we're saying, look, that's not how the formula works. Our formula for the disk method says you find the volume by adding up, which really is an integral, from wherever you start to wherever you stop. And then what? Well, it's pi times the radius of your circle squared times your thickness. Now, that's our formula. Okay, good. Let's use our formula. Let's start with our thickness. I think that's a nice way to think of it. So when we think about our thickness, oftentimes we think about it, what's happening, what is it we're perturbing? What's that small thing we're changing? And for us, it comes down to how we slice. So that thing that we're changing is at what level of y we slice at. So our thickness here is a small change in y. So in other words, it's this little tiny change in y. Okay, good. So let's talk about our bounds now. Because we're going to integrate with respect to y, our bounds need to be in terms of what we're integrating with respect to. So it's not going to be between 1 and e cubed. Those are x bounds. We need it to be matching what we're integrating with respect to. We're integrating with respect to y. So the question is, where do we start and stop slicing with respect to y? Well, what's the y value down here? That's at x equals 1. But the y value, well, natural log of 1 is 0. So that would be 0. Where do we stop? Okay, we stop at the top. Well, what's the y value up there? Well, it actually tells us 3. Okay, so we stop at 3. Good. So we're most of the way there. There's just one little piece left. One little piece left. And that's what's the radius. So we need to start thinking about the radius. Now, our radius is going to be as a function of y, because that's how we're slicing. So we should think about what happens as y. So it should be from this part where we spin out to that curve. Now, currently, our curve is written as y equals natural log of x. That's not a good choice for us. We want to write things as x in terms of y. Okay, so how do we get to x in terms of y? What we do is find a way to do sort of an inverse. If y equals natural log of x, x is e to the y. So I say, all right, so I'm going to go from these two locations. I have the e to the y and 1. All right, so our radius is between e to the y and 1. Question, should we take e to the y and subtract 1, so e to the y subtract 1, or should we take 1 and subtract e to the y? Which one is the right answer? Now, I know some of you are going to say, oh, Steve, it won't matter because we're squaring. I do know that. It won't matter because we're squaring. But there will be times when it does matter. So I want to make sure we get it right now so that we get it right later. It's good to develop habits of doing things in the correct way. All right, so do you have an answer? E to the y, subtract 1, or 1, subtract e to the y? Well, the answer is we want the radius to be a positive measurement, so we always take a high value minus low value. Now, if we think about orientation here, the high value when we go in the left-right direction, high is to the right, low is to the left. So for example, positive infinity is to the right-hand side, negative infinity is to the left-hand side. So e to the y, subtract 1. Right minus left, high minus low. So e to the y, subtract 1. That's our radius. All right, well, now let's just clean it up. So we get that this is going to be pi is a constant. I can pull it out. 0 up to 3. Okay, e to the y minus 1, quantity squared, and dy. All right, so we're set up. Okay, so now that we have our setup, which really is the fun part of the problem, or maybe it's the important part of the problem, we start thinking to ourselves, well, how do we integrate? So what's the right way to integrate e to the y minus 1 quantity squared? Now you might say, oh, well, we'll take the 2, replace it with the 3, divide by 3, and that's the right way to do it, right? Creativity is a beautiful thing in some areas, but with integration you always want to be careful, because the way that the chain rule works for differentiation is not really the way that it works for integration. So you got to be careful, the right amount of careful. So how do we do it then? Well, the way to do it is to start by squaring. All right, so this is pi integral 0 to 3. And if you square that, you'll get e to the 2y minus 2e to the y and plus 1. All right, dy. So a squared minus 2ab plus b squared. Now each part is something reasonable for us to work with. So this would be pi, the integral of e to the 2y. We're going with respect to y. Well, it's e to the 2y. You have to account for the 2 on the inside, so that's a half. Then minus 2 e to the y, so that's minus 2 e to the y. Well, that's the nice thing about integrating e to the y. Integral of e to the y is e to the y, just like the derivative of e to the y is e to the y. Plus 1, integral of that, plus y. And from 0 to 3. Okay, so we plug it in. So we get pi 1/2, 2 times 3 gives us 6, so 1/2 e to the 6 minus 2 e to the 3 plus 3. Good. Are we done? No, because what else do we need to do? We also have to plug in 0. Oftentimes 0 doesn't matter, but sometimes it does. And notice when we plug 0 in, e to the 0 is not 0, so it can make a difference here. So subtract pi. E to the 0 is 1, so 1/2 minus 2 plus 0. Okay, so there we go. Now that's the answer, but let's suppose we wanted to clean it up a smidge, just a little bit, right? So suppose we did that. Well, what would we have? I'll put it over here. So we have pi. Go ahead and pull that out. 1/2 e to the 6. Okay, it's the only time e to the 6 shows up. Minus 2e to the 3rd. Only time e to the 3rd shows up. And then what do we have? We have a plus 3. And let's be careful with this minus. Let's follow that through. So remember, this minus is going to come through to both terms. So and okay. So one way we can think of it is I have a plus 3 and a plus 2, because minus minus 2, that gets us up to 5. And then we're going to have a minus 1/2. Well, if you take 5, that's the same as 10 halves, minus 1/2 would leave us with 9 halves. And there we go. That's the answer. All right. Well, yeah, it's positive. E to the 6 is pretty large compared to e to the 3rd, so we're good to go. All right. Well, what's the moral here? I think this is an important example. It shows us that we can change our way of looking at problems. We're not tied to integrating with respect to x. We can integrate with respect to any variable that's convenient. And we should start thinking about, well, what's the right way to make things convenient? And once we can have that mindset, then we're going to see that the problems become usually a lot simpler and a little bit more fun. The other thing, of course, is remember the generic things. What do the pieces represent? Don't get too caught up in saying, oh, it has to be a function of x squared. Well, no, sometimes it'll be a function of y squared. And instead of trying to remember lots and lots of individual cases, I say, well, the generic formula just says radius squared. And now I say, well, what's the radius in this problem? And then I can quickly adapt. And that helps us be more flexible. And we can get more done. All right, well, this was a lot of good problems. And of course, we'll always do more problems. So keep working and keep getting better. Have a good day.